Welcome to Lecture 1D, entitled Graphing of Scalar Functions. The material for this lecture comes from section 13.6 and 15.1 of the textbook. The objectives of this module are to develop the tools for sketching scalar functions. And the particular concept and visualization skills that you develop through this module are basically the notion of an explicit or implicit function, the domain and range of a function, and different ways basically of visualizing a 3D object. And so one could either do 3D perspective sketches, and there are also three other options, one of them being traces, cylinders, and level curves. Level curves basically are just 2D representations of a 3D system, typically done with only two variables. And we can extend the notion of level curves to level surfaces, which are 3D representation of a 4D object, and we're using three variables to describe the system. All right, as usual, the second slide is just going to be a summary of the contents of this particular lecture module, and these have been itemized here in terms of items 1 through 13. And so we'll just move on to the next slide. Notice though that here that we've got a couple of examples that have been taken from chapter 13.6 and also from chapter 15.1. All right, so we'll begin by basically defining what we mean by an explicit function and implicit function. So on the left you see an explicit function where we have on one side z, and on the other side only a function of x and y. So this is in an explicit form. On the other hand, we can have an implicit function where effectively z and x and y are basically mixed together. So for example, sine of xyz minus zx plus yx would be set to 0. And so this functional that you see here, we're just giving it a label, which is f as a function of xyz. So this is in implicit form. Now we could take an explicit function such as this one and convert it into an implicit form simply by just taking, for instance, the z and bringing it over to the right-hand side, in which case the left-hand side becomes 0. And so this is the expression that you see here in implicit form. So this whole grouping of three terms, x squared, y squared minus z, combined we will basically define as function of x, y, and z. Now here it's a little bit trickier if you want to go from an implicit form in the general case to an explicit. It's not algebraically solvable. So we'll find ourselves quite often in a situation like this, where in fact we cannot actually develop the explicit function. So we basically have to have some techniques that we will develop, which for instance would allow us to determine derivatives of function of this nature, when we know that we cannot take z and put it in terms of a function of x and y. Two other things that we'll consider are what the domain and range of the function. We're considering only two independent variables, call them x and y. In this case, in explicit form, z is some function of x and y. Definition of domain is the permissible values that you can input into the function. That is, what values of x are permissible and what values of y are permissible. Whereas the range are all values that are outputs. That is, what are the permissible values for z given the permissible values of x and y. All right, so let's work on some examples of domain and range. The first example here, z is a function of xy divided by x minus y. The first thing to recognize here is that this function is perfectly reasonable, well-defined except at one point, and that is when x is equal to y. So at x equals y, this function basically has no value. It's undefined, and so it cannot be part of the domain. And so I've written this as x not equal to y, otherwise x and y can take on any value. The range, on the other hand, can be any value in the real number set. So if x is positive and y is negative, you have a negative number. If x and y are both positive, you have a positive number. If x equals 0 and y is some number, you still end up with the value of 0. So you can show that all possible values of z are permissible. Now, if I were to look at the domain and sketch it, then I'd have a diagram that you see here on the right. I'd have this whole region, which shaded in blue. This, of course, extends to infinity, and the fact that I haven't put a very dark line around the contour means this is basically expanding outwards, and I've just shown a small segment. On the other hand, we've just noted that x cannot equal y, which is basically this straight line. And so this red line basically represents the part of the domain that has to be extracted. In other words, you cannot be on any point on this line along here. It's not part of the domain. Let's take another function, the square root of 4 minus x squared minus y squared. In this case, we know that if the argument of 4 minus x squared minus y squared is less than 0, the square root basically is undefined. In other words, there is no real number basically describing the square root of a negative number. So that means that we have to constrain the argument to be a value which is basically greater than or equal to 0. That can only happen if x squared plus y squared is less than or equal to 4. As far as range is concerned, the square root can only be a positive number. And because we've got limits in terms of what x and y can be, it means that there's a limit in terms of the values of z that can be achieved, and those values will be anywhere between 0 and 2. If we were to sketch the domain, that is x squared plus y squared less than or equal to 4, this is a circle of radius 2, but the boundary of the circle is included in the domain. Hence, you'll notice here that's a solid blue line, and this is at radius r equals 2. So this whole region is inside the domain, including the boundary. And the last case is a simple one in which we have a polynomial function. In this case, all values x and y are permissible. And also you can show that for some combination x and y, you'll get values of z which are greater than 0, some less than 0, and for certain range of values of x and y, you get values of z equal to 0. So that means that z can take on any value, and the domain can be any combination of x and y as you choose. And so here the diagram shows an open boundary, and everything in this domain is possible, all possible x and y's. All right, now this is just an aside. This is just a little bit of an expansion on some of the material in chapter 13.6, which deals with quadrics and transformations. And so this general equation that you see here, this is a very general equation that can be used to describe the equation of the ellipsoids, paraboloids, hyperboloids, and spheres. Under arbitrary conditions, that is, it could be a rotated object, could be a translated object, it could be a combination of an object that's been rotated and translated. So this is a very general form. Now, we can basically, using matrix analysis, we can get a matrix representation of a quadric equation, excluding the term gx plus hy plus iz plus j. So effectively what we're doing is we're only looking at the terms that involve products of x's and y's, xz and y of z, x squared, y squared, and z squared. If you would take only this part here, that is, takes it right up to this point here, the product of 2, then we can actually write this expression in terms of a row vector corresponding to x, y, and z components, a matrix having these component values, and a column vector x, y, and z. If you perform the matrix multiplication here, you'll end up with the expression that you see here on the right, which is in fact these first 6 terms of the expression. Now we're going to just let this whole matrix be a matrix N. It turns out, as you'll see, that this is a symmetric matrix. In other words, these cross elements are the same. These cross elements are the same. These cross elements are the same. All right. Under these conditions, we know that we'll have an orthogonal matrix. And in terms of, it will in fact be an orthonormal matrix, and it can be diagonalized. So this is very important because it means that we can represent the matrix N in terms of a diagonal matrix, and also in terms of the orthogonal matrices P and P inverse in this form here. Now, because it's an orthonormal matrix, P inverse and P transpose are one and the same thing. So this happens to be very convenient to have such an expression. A, B, and C are going to be the eigenvalues of the matrix N, and P is obtained from the eigenvectors of N. We basically posted a handout for additional details, which you can find on Quarkus. Some of this material you would have learned last year in linear algebra. I've just put it here in one compact form that you can look at it, but you're not responsible for it. It's just some information that might be useful for those who want to dig into the details a little bit more. All right, here I'm just spelling out the math and the details. Let's say, for example, here, if we represent capital X, Y, Z in terms of a column vector, in terms of P times X, Y, Z in the form of a column vector, then we can basically invert and can represent X, Y, Z in terms of capital X, Y, Z. Just multiply both left and right by P inverse, but P inverse is P transpose, so we end up with a particular expression here. Also, we would have this expression, GHI is equal to P times GHI, or we can multiply left and right by P inverse, but P inverse is P transpose, in which case we would get a column vector, capital GHI is P transpose GHI. So we can also write that the transpose of a column vector is a row vector. So this is for the capital GHI, and this is for lowercase GHI. This is just preliminary information. And so that means that if we take the transpose of this column vector of uppercase characters, right, this can be represented in terms of P transpose column vector GHI lowercase transpose. If we do this, we end up with this expression here. Don't forget, when you take the transpose of a product, you take the transpose of the first object times the transpose of the second object, and you get a row vector, and the transpose of a transpose is the original. So that implies that we can represent this expression here in terms of this expression, which simplifies to this expression. So this and this are equivalent. So on the basis of that information, we can then take the original expression we started with on the previous slide, and now we can basically represent in transforms coordinates as this expression plus this expression plus the leftover term, which is j, and that was equal to 0. The next step is to complete the squares on the right-hand side. All right, and so what we're doing is taking this expression and writing it out as x minus x naught squared, y minus y naught squared. Right, so this purely is in terms of squares of functions. Right, and this basically is equal to the expression that you see here. But in order to have a match between the two, x naught takes on this value, y naught takes on this value, and z naught takes on this value. Assuming a is not equal to 0, b is not equal to 0, and c is not equal to 0. Now, of course, there are special cases, a equals 0, b equals 0, c equals 0, a equals b equals 0, a equals c equals 0, and so on. So this is just an illustration. If a equals 0, then we will see that this expression simplifies into this form. So a sample of quadratic examples in an unrotated and untranslated state are given on page 862 of the textbook. All right, so now let's look at the different techniques used to try to visualize a 3D object, the first being traces. All right, so what's the motivation? Well, it's easier to construct multiple 2D objects to form a scaffold over a single 3D object. And so the technique is one of first drawing a 2D cross-sectional view of a 3D graph for a specific plane. And the simplest planes to consider are the XY plane, the YZ, or the ZX plane. Of course, you can choose other planes as well, but these are the ones that typically are used. So the example we're using is the one that's shown here on the right. This is basically the equation of an ellipsoid, which is centered on the origin. So what we do is we do 3 different tests. In one case, we set z equals to 0, and we do a graph. The next case we do is y equals 0 and basically sketch the graph. And the last is to set x equal to 0 and sketch the graph. So you'll see when you set z equal to 0, this is reference to the xy trace. When you set y equal to 0, it's reference to the xz trace. And when you set x equal to 0, then that's equivalent to the yz trace. And so that's all we've done. By substituting z equal to 0 into the original equation, you have now a function purely of x and y. Here you have a function purely of x and z. And here you have a function purely a function of y of z. The first picture just shows the illustration of doing the xy trace, which is basically plotting this equation which is an ellipse in the xy plane. Then if you perform the other two, you can put them all on top of each other. So this is the xy trace, this is the yz trace, and the green line is the xz trace. If you put three together, this forms a scaffold, and you can then sort of approximate what the surface of that ellipsoid would look like. There is an interactive visualization that you can access here. This is from the textbook. I'm just putting it here for your reference purposes, so we can move on. All right, here's another example. This is from chapter 13.6, question 13. You're given the function z is equal to ln of y, and x is an element of R. Now, sometimes you're just given the function, and it's implied that if x is not mentioned, that x is an element of the real number set. And so if we're to graph this object, you can see that it's in blue. It's this object that you see here. Now, if I want to do a zy trace, right, a zy trace basically means that I would set x equal to 0. All right, so if x equal to 0, then I'm basically just graphing a line which happens to be on that surface that you see there. All right, and that's the line that's shown in red. If you want to look at this from a visual perspective, you can go to the link that's shown here. All right, let's look at elliptical paraboloid. This is from chapter 13.6. Elliptical paraboloid would have an equation of the form here. It's elliptical because you have an x squared, y squared, and you have denominators which have two different values. It's a paraboloid in the sense you've got z is a function of a square. Okay, so it's a combination of two. If z is greater than 0, then it's an elliptical paraboloid that opens up. So it has this sort of a shape to it. On the other hand, if z is less than 0, it's an elliptical paraboloid which opens down, which means it looks like this. Okay, so the value of z sort of gives you an indication of whether it opens up or opens down. If you want to look at this object, you can basically click on this link here. All right, so this is another example. This is question 23 from chapter 13.6. In this case, the function is y equals x squared over 6 plus z squared over 16. Again, this is an elliptical paraboloid. And so we're looking at a couple of examples. Want to sketch what the xy trace would look like. And we'd like to look at the xz trace, but in this case, we're going to choose a value of y equal to 0.25. So conventionally, we would not necessarily call this an xz trace because usually imply y equals 0. But here I specified it's a trace with a specific value of y. The xz trace is basically when we set y equal to 0, and the yz trace is x equals to 0. So if I choose an xy trace and set z equal to 0, that means I set this term to equal 0, and so I'm graphing y equals x squared over 6. This is a parabola, and you can see it's the yellow line that you see here. Xz trace for y equals 0.25. That means I would let y equal 0.25, and then I'd be basically graphing here what appears to be an ellipsoid. And so that's the object you see in black. On the other hand, if I set y equal to 0, then this would be x squared over 16 plus z squared over 16 equals 0. This will only have a value of 0 when both x and z equal to 0, which is right at the origin, so that corresponds to the black dot that you see there. Lastly, a yz trace with x equal to 0. If I set x equal to 0, we just have y equals z squared over 16. So this is also a parabola, but this one basically is the one that's shown in red, which is basically on the zy plane. Okay, hence yz trace. Again, the link you can see is up at the top of the page. All right, question 35, chapter 13.6. This is a function z equals x squared over 9 minus y squared. Okay, so this has a hyperboloid characteristic to it, but also a paraboloid characteristic because it z is a function of the square of 2. So let's look at three different traces: the xy trace, which is when z equals 0, xz trace when y equals 0, and the yz trace when x equals 0. When z equals 0, we basically have y squared equals x squared over 9 But if you take the square root of that, then there are two possible solutions to that because of the fact it's a square, plus or minus 1/3 x. So these are two straight lines, slope of positive and a slope of negative, shown in yellow. So you can just see the lines are here, and those two lines are on the xy plane. Let's look at the xz trace with y equals z to 0. That means you end up just with z equals x squared over 9, which is the term that you see here. This is a parabola, and so this case is shown in red. This red basically would be in the xz plane, which is the red line that you see here in the form of parabola. And lastly, the yz trace when x equals 0. You have z equals minus y squared. This would be in the yz plane, and so it's this orange parabola that you see here. It's basically going down because it's got a minus sign here. Again, if you want to look at this from a visual perspective, you can click on the link over here. All right, so we have one example here. Another one, this is example 5, chapter 13.6. This is function z equals x squared minus y squared over 4. Again, similar characteristic to the previous one. In this case, if we set z equal to 0, that's the xy trace, then we'll end up with a solution y, two possible solutions, plus or minus 2x, which are the two lines that you see on the xy plane. Xz trace is when y equals 0, then z equals x squared. And so that's this parabola that you see here on the zx plane. And lastly, yz trace is when we set x equal to 0. In this case, this becomes z equals minus y squared over 4. And so this is the orange parabola that you see here. Again, it's a negative. All right, the next thing to consider are cylinders. And what do we mean by cylinders? All right, so definition. One variable in the function is missing, which means the function holds all values of the undefined variable. You have the same trace at any point you pick along the zeroed axis. So for example, if fxy equals 0, or gxz equals 0, or h of yz equals 0. Okay, so this is basically indicating that it's not a function of x here, it's not a function of y here, not a function of z here, which means z can take on any value. Here, y can take on any value, and here, x can take on a value. So let's take this example. X squared plus 4y squared equals 16. In this case, z isn't mentioned, which means z can take on any value. So if you were to sketch this example, this is more or less an ellipse in the xy plane. And so you take the particular object and you extrude it along the z-axis because it can take on any value. All right, so if we look at the domain of this function, this is x squared plus 4y squared equals 16. All right. However, this value can be, x could be any value between minus 4 and plus 4, and y can take on any value from minus 2 to plus 2. Of course, it's restricted by this equation in terms of what values it can take on, but nevertheless, these are the range that you can get and the range of y that you can get. And z basically, as I mentioned, can take on any value. So when you draw the trace in the xy plane, it's just a red line. And then you take this and you extrude it along the z-axis. And so this black line is basically another trace taken at a different value of z. You put these all on top of each other, basically to create a scaffold. And from that, you can determine that you're actually looking at an ellipse. And that ellipse has been extruded along the z-axis. All right, you can also see a visual version, interactive version of this if you want by just clicking on the link here. This is from the textbook. All right, next is level curves. So level curves, something we deal with when we're dealing basically graphing a two-variable scalar function. And what are they? They are projections of the function onto the xy plane for different values z, which you select. So z equals fxy, we hold z constant, and as a result, you're plotting y as a function of x for a particular value z. You then repeat the process for different values z, and essentially put the plots one on top of each other, but they all appear on the xy plane. So for example, if we have this Gaussian function, z is equal to e to the minus x squared plus y squared, if we were to graph this for various values of z, this would involve basically a series of circles, right, with origin at the center. And so, for instance, if you look at this particular graph, for z equals 1, right? You put 1 here, and you basically determine what x and y would be given z equals 1. And you would end up basically with the blue. If you talk z equals 0.8, that means 0.8 goes in here, and plot x as a function of y, you would end up basically with a circle, again, but of a different radius. Z equals 0.6 would be red. You'd end up with a circle of the radius, which corresponds to this red circle. Z equals 0.4 black. This would basically be a circle, give you another circle. And Z equals 0.4 orange, which would be the outer one. So starting here, that's basically a single point, and then eventually at z equals 0.4, we end up with a circle, which is orange. If we were to look at this in terms of a cross-sectional view of this function, which is what you've shown here, here's the Gaussian function. And so if you have z equals 1, you're probing the top of the function. There's only one point here. That corresponds to the blue point. On the other hand, if you choose z equals 0.8, cut across, then you're probing this point here and this point here. But of course, this is just a slice through in one direction. If you go rotate all the way around, you'll be tracing out the circle. Similarly, the red line is for level curve at z equals 0.6. Notice here, the radius gets larger. And so that's this red line that you see here. All the way down to the last case, z equals 0.2, which is this orange line. And that leads to the largest circle. All right, so these are the basically level curves. Now, one other thing to note is that the spacing between these curves, if base values of z are equidistant to each other, will tell you something about how the function is changing. If these particular circles are close to each other or equidistant with respect to each other, then basically the slope basically is the same no matter where you're going. On the other hand, if you see a lot of bunching, that means that there's a sudden change in the slope. The function's either increasing rapidly or decreasing rapidly. So this basically brings me to the example 2. This is a topographic map, which is an elevation diagram. And if you look here, these lines that you see here are lines of constant elevation. Okay, so it's a projection of a 3D object onto an XY plane. Now you can tell here that the lines are close to each other, so this appears to be something with a steep embankment. And you'll notice that the lines on this side and the lines on this side are separated from each other. So this represents a canyon through which a river is flowing. And so this type of diagram allows you to visualize what this thing would look like in 3D. Right? So these would be lines of constant elevation, and typically they'd be equidistant. So they might be basically 1,000 meters apart or 500 meters apart. But the density, in other words, how rapidly or how many you get in a small region, tells you whether or not there's a sudden change in height. If it's basically spaced far apart, means it's a very gentle slope. All right, so let's take an example of scaling, of graphing level curves for a two-variable scalar function. And I'm taking this potential function in the xy plane of two 3D point charges. So one point charge is located at 0, 0, and one at 1, 0. And so first thing to do is determine the domain of this function. Well, clearly, the denominator cannot be 0 here, and the denominator here cannot be 0, which means we have to exclude the point 0, 0, and the points 1, 0 from the domain. Otherwise, all values of x and y are permissible. As far as z is concerned, the square root can only be a positive number. There's a positive number here. So z is always going to be an element of R, but it's going to be greater than 0. It can't be exactly equal to 0, because for that to happen, the denominator has to go to infinity. And we cannot define infinity, so we just say z is greater than 0. So when we graph the domain, we can see everything is permissible. It's an open boundary because it goes to infinity. But these 2 points have to be excluded from the domain. All right, so if we were to graph this picture of the level curves, what we would end up with is this particular figure here. And I'm going to talk a little bit more about sort of simple techniques we can use to establish what we call asymptotic limits. In other words, situation when you're very close to the points of interest, which are excluded from the domain, and when you're far, far removed from the points that have been excluded from the domain. So if you'll see here, this is an actual picture, a 3D perspective. These are the points at which a charge exists, which means a potential basically blows up at this point and it blows up at this point. If you take level curves, you're just slicing through the object and you're plotting basically what the value of y is as a function of x. Close to this point here, which is the 0, 0 point, you notice that these level curves take on almost pure circles. Now, why is that? Well, because at this point here, this term dominates over this term. So to first order, you can essentially approximate the function as being 5 equals 2 over square root of x squared plus y squared. But this is nothing more than the equation of a circle of a specific radius. If you're close to this point, then this term dominates over this term. So this now becomes a circle centered on the point 1, 0, right? And this is equal to 5. As you get further and further out, then of course both of these terms play a role, and so you see this funny particular pattern that exists. Now if you go further and further out, then this sort of starts to become elongated, and if you go very far out, then these 2 points appear to be getting closer and closer to each other from the perspective of an observer far, far removed, and so these start to approach that of a circle. So that gives you some idea in terms of, what we're looking at when we try to imagine how you would sketch the level curves. So this is just an illustration that you can basically make use of. In the textbook, it's an interactive simulation. All right, and so this is basically what I mentioned on the previous slide, the notion of asymptotic approximation. This is again example 6. So what I've done here basically is shown you the 3 possible scenarios. One when you're close to this point, one when you're close to this point, and when you're far removed from both of these points. And so these are the simplifications that one can make, from which one can come up with simple equations representing close in, these are circles of a certain radius, close in, circles of specific radius, and far removed, although we can't show it here, you can essentially say this looks like a circle which is displaced by 0.5 units along the x-axis. All right, so the last thing we want to look at is when we extend to 3 variable functions. In this case, we'll be dealing with level surfaces, because what we're doing, we're saying that w is a function of 3 variables, and now we're holding w to be constant, but we choose different constant values and basically replot the function x, y, and z. So if you can write this in explicit form, then presumably you will be able to say that z is some function of x of y for a specific w value which is constant. So what you'd be plotting out is a surface. So w equals 3 might give you this type of surface. W equal 2 might give you this type of surface. So this would be, for instance, if we're dealing with w having this form here. And then w equals 0 would be this particular surface. So the level surfaces could be used to represent an object which is 3 variables. And from this you can imagine how you would extrude this out to represent this in terms of a 4 variable. Of course, you can't graph it, but the concept is the same, that you can basically move from level curves to level surface. Just means you're raising the dimension by 1. And there's an interactive version of it here. You just click on this and you can play around a little bit with it as well. Well, that concludes lecture 1D. Thank you for listening.